Okay, guys. Hi. I think this clock is a little late, right? We're already at the time. So I'll just start because I have a lot to talk about. Actually, my presentation is a little bit longer than the 45 minutes, as opposed to most of the other talks that we've seen today. I wanted to fix that last night, but then I realized that all my animations within the keynote were kind of destroyed, broken, because, and that's my main advice that I want you to take away from this talk, do not update Keynote or PowerPoint the week before your presentation. Bad idea. Okay. One other thing I noticed, it's actually pretty cool to have a microphone back in my hand. I used to be a radio reporter 2.5 years ago, and it's the first time that I'm actually using a real microphone again. This is cool. By the way, you're listening to KISS FM, the hottest hits in town. Okay, one other observation I made, like the waiters here, when you have a coffee, and you just finish the coffee cup, it's immediately gone. You know what that is? That's automatic reference counting, you know? The moment you lose your strong reference, it's gone. Yeah, no, I didn't say that. I no reference here. Okay. So the original title of this talk was Auto Layout from Leading to Trailing. And I was very proud of that name. I thought this is a really great title because it incorporates these layout anchors, leading and trailing. And it also sounds like from A to Z, like incorporating everything you need to know about auto layout. And then I presented it to a couple of people at local meetups, and then someone told me that this might not even be the best name for a presentation, right? Because from leading to trailing also means something else, right? It means falling behind in a race, right? Like this. I was probably a little bit too constrained in my thinking. But luckily, there's an easy fix for this. I just did this, right? I just swapped trailing and leading, and so now this is the official name of the talk. So that's the goal of this talk, to help you master auto layout. So let's begin. My name is Mischa Hildebrand. I'm an iOS developer at Kupferwerk. It's a company based in Munich. We create iPhone apps for other companies, and yeah, it's a pretty nice place to work at. So auto layout is a mysterious thing to many people, right? It sounds kind of easy, it looks easy, but then there's all these different methods that all sound very similar, but you never really know which of these methods to choose, right? And you have a particular layout problem and you want something to update, but you end up trying out every single one of those methods and then combinations of those methods. And then you get really angry because nothing really works, right? So auto layout is like a huge black box, and no wonder there's 2 sessions at WWDC 2 years ago, I think, or 3 years ago, that were called Mysteries of Auto Layout, Part 1 and Part 2. And today I want to kind of get rid of some of those mysteries and get clear answers to that. The first news is we can get rid of that method set needs display at the bottom because it's not related to layout at all. I saw some people using that and they were trying to achieve layout problems, but it's not related to layout. So the question is, what is layout? Well, an iOS layout defines what to draw and where to draw it. It does not define how to draw it, right? That's what set needs display does. So let's have a look at an example. I created this wonderful iPhone app. Very proud of this. Still old navigation bar, but okay. And then we decompose the user interface into all these individual components, and that answers the question, what? We have navigation bar, profile image, name label, etc. Right? And then this whole thing is embedded in the system's coordinate system, in the device coordinate system, right? And this answers the question, where, right? If we pick an individual component, like the name label here, for example, and we have its origin defined by its x and y value, and its width and its height. So we have the origin and the size, and these things compose a view's frame. So far, so good. Most of you probably know all these things. So to put it simple, layout is just another word for determining the frames for all views on screen. That's what it does. That's the process. How do we do that? Well, the classic approach and the easiest approach would be to just write down the layout manually, to just specify all these coordinates directly, like that. That's how we used to do it several years ago when we only had one particular device size, right? But now we have all sorts of different device sizes, right? We have the iPhone 7, 8 Plus, and the iPhone 10, and the iPhone SE. So what happens if we use the same code for another device? This is what happens, right? We specified the original coordinates, but the screen size is bigger, so eventually the relative portion of the button relative to the screen is much smaller. And that's usually not what we want. What we would want is that the button resizes so that it has a fixed padding on both sides to the screen, right? But with manual positioning, this doesn't work. And that's why we have auto layout, right? With auto layout, we choose a semantic approach to describe our layout, right? Which is we want a fixed spacing on both sides of the button to the screen edges. And now if we resize the device or choose a different device, then the button automatically adjusts the way we want it to do. So we have an adaptive user interface. Now these tiny blue lines, as you all know, are called constraints. And they are always attached to something, right? These handles on both sides, they need to be attached to something because otherwise they don't have any meaning, right? And this something is called layout anchors or layout attributes also. So we have two horizontal layout anchors, leading and trailing, and we have two vertical layout anchors, top and bottom, right? Why is this called leading and trailing and not left and right? What? Language. Exactly, yeah. So there are some languages. This is only correct for languages that read from left to right, like English. And then there are also some languages like Arabic that read from right to left, and for that language, they're just swapped. So if you use leading and trailing instead of left and right, your layout will automatically adapt to the reading direction of the particular language. So these layout anchors are the base layout anchors, and that's really important to know. From these layout anchors, you can deduce all other layout anchors, and that's what we're going to do next. We have dimension layout anchors, the width and the height. So as you can see, these are deduced, expressed through the base layout anchors. And then we have the center layout anchors, the horizontal center, which is pretty much the average of the leading and the trailing layout anchor, and the vertical center, which is the average of the top and bottom layout anchor. Of course, obviously, we need to take the absolute value of this, but I try to keep it simple here. So, and then there are some special layout anchors that are interesting for labels and text views, and they only work on these. It's called first baseline and last baseline, and it's pretty self-explanatory what these things do. Now, with all these definitions, we can just have a look at some examples, what we can do with it, by simply writing down an equation, equating these layout anchors. So here we can align two views on their left side. We can also define that the width of two views should be equal. And if we add some constant, then we can add spacings between the views. Or we could also define a particular aspect ratio on a single view by applying a multiplier here, square root over 2, right? So all these formulas at the bottom, they follow, of course, a simple pattern, and this is called the constraint formula. And this is the general form of the constraint formula. Every single line you see in Interface Builder is just a visual representation of such a formula, right? And as you can see, it's a linear equation, so the kind of equation that describes a straight line. You all know that from school, right? Same pattern, very simple. Now the interesting question is, how do we get from the constraints to the actual frames on screen? Because in the end, we need to draw our views on the screen, right? And we need to know the actual coordinates, the frames of the views. So how does this happen? Well, short reminder, these coordinates or these parameters are a view's frame, and these are the base layout anchors, and we can express a view's frame in terms of the base layout anchors this way, right? So knowing these 4 base layout anchors is equivalent to knowing the view's frame, right? So once we've found the positions of all layout anchors, of all base layout anchors, we have succeeded in finding our frame as well. So that's our mission for now. Let's look at an example, right? We have a very simple layout here, just our root view, which is the screen in this case, and we have only one view inside. And now let's add some constraints. We add a leading constraint with a 8-point padding, then we add a trailing constraint and a top constraint, and then we require that the height of this view is always equal to 20 points. Okay, so far so good. Now, as you can see, I colored the base layout anchors here in the upper 3 equations in blue. But in the last line, we have a layout anchor which is not a base layout anchor. It's a height thing, which is a deduced layout anchor. So what we need to do in order to solve this system is to replace the height layout anchor with the base layout anchors here. So let's do this. Right? So now we have a set of linear equations. We have 4 equations with 4 variables, and there's some fancy rule in linear algebra which says that this is solvable if a root view's base layout anchors are known, right? So if we have 4 equations, 4 variables, this is solvable. So what's missing here is like the root view's base layout anchors, these guys here, root view leading, etc. How do we get those? Well, fairly easy. We know the root view is like the screen pretty much, so its origin is obviously 0, 0, and its size is determined by the screen width and by the screen height. So on the particular device, we can simply substitute these values. And then we put them back in the equations, and this is how we get the base layout anchors for view 1. The last equation, root view bottom, we don't need it here, so let's get rid of it. And that's was only possible because we already knew the values of the super view's base layout anchors, right? So the screen layout anchors. And that's a general rule, right? If a view knows its own frame, it can compute the frames of all its subviews. The outermost view, the outermost frame is always known. It's the Windows frame or the screen, right? And that's the reason why the layout flow is always from top to bottom. It goes always from super view to subview, right? We start with the screen, then we lay out the subviews, and then these subviews lay out their subviews, etc. So super view to subview. It's important to remember. So now let's make our user interface a little bit more interesting by adding a second view, and then we add several constraints. Well, okay. So as you can see, this is still a very simple layout of an iPhone app, and we already have so many equations. And for each view, we'll get 4 more layout anchors. So that's a dozen of constraint equations. That's you don't want to solve them. I don't want to solve them. It's ridiculous. So the good news is that the system does this for us, right? The system computes the actual frames of all subviews by solving a set of linear equations, and that's exactly what happens inside the UIView method layout subviews, right? It takes the constraints and transforms them into frames by solving all your constraint equations. All this happens during a so-called layout pass. What's a layout pass? Well, a layout pass is some abstract thing, a black box again, of which we know that at some point during the layout pass, layout subuse is called. Right? So whenever the system thinks it's necessary to go for another layout pass, it triggers another round, and this happens again. Right? So the constraint equations are solved in order to compute the actual frames over and over again whenever the system thinks it's time again. Layout cycle. Now the problem is that you never really know when a layout pass happens because the system decides that, right? But sometimes you need to trigger a layout pass yourself. How do you do that? Well, the first thing that comes into mind is call layout subviews, because we just learned that layout subviews resolves the constraints into frames. Right? That would be the first idea to come up with. But please never do that. Never call layout subviews yourself. Instead, call this method layout if needed. Right? And why? Why shouldn't we do this? Why shouldn't we call this method directly? Well, it turns out that it's due to performance, right? Because layout subviews will always solve the set of all your constraint equations, even if nothing has changed at all. The same set of linear equations would be solved over and over again, wasting processing power and memory resources. So it's a way better idea to keep track of the changes to the constraints and to the view hierarchy. And then only if something changes, then you invalidate the layout. And then during the layout pass, you call layout subviews only if the current layout is invalid, if you've invalidated in the previous step. Right? But how do we keep track of the constraint changes? How do we know if something has changed? Well, it turns out there is an internal flag for this. I just call it needs layout. Someone at UIConf told me it has a similar name internally, but something a little bit more difficult with underscores, etc. Let's call it layout for now. And it doesn't really matter because it's internal anyways. Okay, so this flag has two states. It has a valid state, which means that needs layout is false, which means that all frames are properly set. And then it has an invalid state, which means that some frames are not up to date and need to be recalculated. Now, when I told you that layout subviews is called by the system during a layout pass, I wasn't entirely honest, because it's only called if this internal flag needs layout is true, right? If not, layout subviews is just skipped, right? And that's very important to remember. If needs layout is false, layout subviews won't be called. So one disclaimer up front here. This is not Apple's original implementation. It's just a way to think about this, to make it easier to understand. This is pretty much how to think of this method, right? That's what layout if needed does. So now the important question is, how do we raise this flag? How do we invalidate the layout? Well, most of the time, everything happens automatically, right? Needs layout is automatically set to true whenever you add or remove constraints, when you modify existing constraints, or if you add or remove a view to or from the view hierarchy. And when is it validated? When is the flag pushed down again? Well, obviously, after the layout has just happened, right? After each layout pass, we know that the layout has now been resolved and everything is okay. So when layout subviews has returned. So most of the time, you don't need to bother about invalidating the layout or anything because it happens automatically. But there are, of course, exceptions. In some cases, it might be necessary to manually invalidate the layout. For example, when you change a label's text and you want it to resize. And then you need to call set needs layout. What this does is it raises the flag, it pushes up the flag. It invalidates the layout. Yeah, so it sets the internal flag, needs layout to true, and we'll force a layout subviews call in the next layout pass. We'll make sure that layout subviews won't be skipped. So now it's kind of obvious that a combination of these two methods, first set needs layout and then layout if needed, will trigger an immediate call of layout subviews, right? First we invalidate the layout and then we lay out if the layout has been invalidated. Pretty simple. And now it turns out that this pattern of invalidating something is pretty common in UIKit. And there's another method, I call it the principle of invalidation, which works the same way. There's set needs update constraints, and then there's update constraints if needed. Same principle, this will trigger an immediate call of update constraints. Now, the question is, what does this method do? And I think I have 26 minutes left, I think, so I'll skip this for now, and if we have time in the end, I'll be happy to explain it to you, okay? So because like the most important part I want you to take away from this is that in 99% of the cases, you should never touch this method, and you should never try to call any of set needs update constraints and update constraints if needed, because most of the time everything happens automatically. I rarely ever needed to use that. So, but there are some cases. I'll skip it for now, maybe we have time later. Oh, that was wrong. How do I skip it? I'll manually skip. There we go. There's still one piece missing in the puzzle, and that's the intrinsic content size. Constraints are really good to define layouts because they give you a lot of power and control. But when you use constraints, you always need to make sure that when you place a component on screen, that that its position and its size are absolutely defined, right? So when you add a second component of the same type, a second switch here, you'll have to do the same thing over and over again. You'll have to add a width constraint and a height constraint, which are obviously the same. It's kind of redundant information that you're putting into this. You're adding extra constraints that you wouldn't even need, right? So this gets ridiculous the more UI components you add to your user interface. It's always the same size, and therefore we have the intrinsic content size. The intrinsic content size is a view's natural size, the size it prefers to take. There are several UIKit components that have an intrinsic content size, like the UI switch we've seen before. The UI activity indicator comes in 2 different sizes, depending on what you choose. You have the UI button, which has an intrinsic content size that's equal to its contents, to the text it encloses, plus some padding. The UI image view has the size of the image it holds, or if it doesn't have any image, then it doesn't have an intrinsic content size at all. Then you have the UI label, which whose intrinsic content size is the size that just fits its text, right? And if the label's width is not constrained, then it doesn't have any information on how wide it should be, so then the intrinsic content size is equal to the size of the text if you put it all in one line. And then you have the plain UI view, which has no intrinsic content size by default, but subclasses can define their own intrinsic content size. So whenever you use subclass UI view, you can define your own intrinsic content size. Let's see how we do this. So we simply override the intrinsic content size and then return a size that suits our view, right? Very simple. If you only need an intrinsic content size for one dimension, so for width or for the height, then you simply return this constant UI view no intrinsic metric for the other component. So this would mean that our view only has an intrinsic height, but no intrinsic width. So when does this intrinsic content size come into play? Well, it is applied when a view's size is not fully determined by constraints. So if we have a view in our root view which has an intrinsic content size as defined here, and then we add only constraints to specify the position, so a leading constraint and a top constraint, then the view size automatically adjusts to the intrinsic content size. Now if we add another constraint, the height constraint, then the intrinsic content size is kind of overridden, right? So the view resizes to satisfy the constraint that we add. And for the other dimension, it still uses the intrinsic content size. So the width is still 50 in this case. And that's pretty much a general rule that you should remember. Constraints that you add on a view always come first. And the intrinsic content size is kind of a fallback thing. If you don't add any width or height constraining constraints, then the intrinsic content size of that view will be used if the constraint priorities are high enough, okay? So if you have constraint priorities by default that are required, so a value of 1000, then this rule always applies. If you, of course, reduce the priorities of the constraints, this rule doesn't hold any longer. And this is my general tip. Use the intrinsic content size whenever you can. Because, yeah, it pretty much represents the view's natural sizing behavior, and you have less constraints to worry about that can potentially conflict with each other. So how does this intrinsic content size even work? Apple once said that everything since the introduction of auto layout is constraints now. So there is nothing, everything is defined by constraints, even the intrinsic content size. And that's actually the truth, because the system creates constraints from the intrinsic content size that happens internally. So if you have an intrinsic content width of 50 here, then at runtime, the system will create a constraint with exactly this width, right? Now, what happens, I just told you, if we add constraints in Interface Builder or in code ourselves to a view, then these constraints always take precedence. But in this case, this wouldn't be the case, because we would have conflict here. Two constraints which say different things. And that's what we have layout priorities for, right? Constraints can have priorities. The lowest is 1, the highest is 1000. And inside layout subviews, the layout engine computes the frames like this. That's what these priorities are good for. We start with the highest priority at 1000, then we resolve all constraints with this priority. Then we check if the layout is still ambiguous, right? Or if it's already clear where all our elements should be positioned. If it's still ambiguous, then we reduce the priority by 1, and we start over with step 2 and resolve all the constraints with that priority. And then we ask again, is the layout still ambiguous? And at one point, it won't be ambiguous anymore, and that means that the layout is finished, and we return from our layout subviews function. So it's important to know that these layout priorities or constraints with a priority of 1000 are called required constraints. That's what they refer to in the Apple documentation. And constraints with a lower priority are called, or I call them, fallback constraints, because they won't cause any layout conflicts that you'll see in the console. And the fallback constraints only apply when all required constraints produce an ambiguous layout. The standard priority for constraints you add in code or in Interface Builder when you don't change anything is always required. So you always get the 1000 priority. And for system-generated constraints for the intrinsic content size, it's fallback. So it's lower than 1000. And that's how we resolve the conflict back here, all right? So the system-generated constraint is fallback. So the Interface Builder constraint in this case will take precedence and everything is fine. Okay. So now that's, again, only half of the truth. Because unfortunately the world is not that simple, because this constraint at the bottom, the system-generated one, it's actually not one constraint, it's two constraints. And they look like this. There's one constraint which it's inequality constraints, as you can see. The first constraint says the width has to be greater or equal 50, and the second constraint says that the width has to be smaller or equal 50. Now, the first one, greater or equal 50, is called compression resistance. Why is it called compression resistance? Because it says it has to be greater than something. It's trying to push, there's a force that's trying to push the view greater, to make it bigger. And the second constraint, the lesser or equal 50, is called the content hugging constraint, because it's trying to pull the view together. It counteracts the other force that's trying to resist the compression. So now we have these content hugging and the compression resistance. Those are the constraints, and they have a different priority. Content hugging is 250 by default, and compression resistance is 750 by default. Why is that? Well, obviously, it's more important that UI components don't get compressed, so you cut off any important content that you want to display, and it's not that important that view always stays as close as possible, as small as possible. And you can even set these priorities in Interface Builder, and that's what actually happens when you enter these values down here. It's priorities for existing constraints that are created by the system during runtime. Now, why should you even bother changing these content hugging compression resistant constraints? Well, to avoid ambiguity. If we have two labels in a row, like here, in a fixed root view, and we constrain them horizontally like this, and then this would be the intrinsic content size of the two labels, right? Because the intrinsic content size is just the size that encloses the contents of the labels. So now we have a problem. We don't really know which one to choose. We could choose this solution where the first label just is hugging itself more or less, and the other label resizes. This would be a valid solution for this layout from the constraints. Or we could also do this, right? And that the second label hugs its contents. It's both valid solutions for our constraint-created layout. So this is ambiguous. Now we need to resolve this ambiguity somehow. We need to define which label is more important for us to hug its contents, right? Which one can expand, which one should hug its contents. And that's what this content hugging priority is for. We just increase the content hugging priority of the first label, and then it's not ambiguous anymore. And it will always end up with this solution. Now there's another example for the compression resistance. We take pretty much the same example again. We have two labels which should display the results of a football match. Now the original contents of the labels would be this. You can see the first label is truncated a little bit because the contents don't fit inside the label right now. Now both labels have a default compression resistance of 750. Obviously, both the labels don't fit in one line. So again, we get the problem. Even so this will be ambiguous again. Even if we kind of tried to put the whole content of the first label inside, it still wouldn't be enough space, as you can see here, right? So now we increase the compression resistance of the first label, and then this always takes precedence. But this is usually not what we want to achieve in this case, because for football fans, it's usually more important to see the results than the whole name of the first football team, right? Probably we are already aware of this. So in order to make that sure, we just reduce the compression resistance of the first label, or we could also increase the compression resistance of the second label, and then we can make sure that the results will always be displayed no matter what. And that's what CHCR, content hugging compression resistance, is all about. Um, some advice on how to choose your layout priorities. Don't use random priorities like these, okay? Even if they're not 347 or something, some people write like something like 800 or something. It's not a good idea. Use the system defaults instead. There are these 3 or 4 system defaults. We have required, as said. We have a default high, which is 750, and we have a default low, which is 250. If you need to change them because you have conflicts like with content hugging and compression resistance, then only slightly increase or decrease these values. You can use the constants up here in order to do that. For example, use 249 or 251 for content hugging, or 749 or 751 for compression resistance. And the reason why you should do that is that it's because when you get really complex layouts, you might need all those numbers and you get really confused with all the different values. Why should you choose? And it's not really explainable why. It's only important that the priority of 2 labels which are in a row, for example, are different. It just has to be like whichever one is higher wins. So if you have 3 labels in a row, you might choose 749, 750, and 751, for example, right? Okay, one more thing at the end of the presentation. Any one of you seen this before? Hands up, who has? Okay, that's all real iOS developers here. Okay. It's like the layout system is mugging you. I hate these things. It's like the system playing games with you. It's really annoying. But it's very important that you stay cool about this. And one way to do this is to look closely at what these logs tell you. There's this thing called NS auto-resizing mask layout constraint. And whenever you see that in the logs, you get a hint of what might have gone wrong. And it's related to this ominous property called translates auto-resizing mask into constraints. It's a really fancy name for a property. And I know it's really very precise. One must leave that to the Apple developers, but no one really understands what it does. Like most of the people, when you read it, like what does this even do, right? So it's so precise that 99% of the developers don't understand what this is doing. So what's it all about? Well, you can think of it as a toggle. It's a simplification, but it's a very useful simplification. Oh, yeah. That was to indicate that most of the layout conflicts are triggered by this setting or not setting this property. So translates auto resizing mask is a toggle between auto layout and manual positioning, right? And when you know that, then all the conflicts go away. So if we switch this property off, and that means that we use auto layout. That means that if you set the view's frame, this will have no effect. Why? Because if you set the view's frame manually, then in the next layout pass, the constraints are resolved, a new frame is computed, and the frame you just set is overridden, right? So with auto layout enabled, you cannot manually set a view's frame because it will just be overridden in the next layout pass. Now if you choose manual positioning by activating this property, then the system will create constraints at runtime that kind of emulate a fixed frame, like we saw with the intrinsic content size, with content hugging compression resistance. And now you can set the frame directly, right? Like this, like we saw in the beginning, and it won't be overridden in the next layout pass. So you can still do that. If you want to do manual positioning, make sure you enable translates auto resizing mask into constraints, set it to true. Now I want to finish with 2 simple rules that you should remember in order to avoid constraint conflicts. First one, if translates auto resizing mask into constraints is true, don't add any external constraints to the view, right? Because the view's size and position is already fully determined by its frame, and you'll get conflicts if you still constrain it. And the second rule is very important to know, that views you create in Interface Builder always have this property set to false automatically, right? But for views you create in code, this property is automatically set to true, right? So that's really important to remember, because otherwise, if you don't take care of this property, you'll end up with this again. Okay, so that's our tour today of auto layout. I hope I could transport some knowledge about this, and you'll be able to take on the lead in auto layout. I have 6 more minutes to go. Do you want? Yeah. You want to go? No, I have 5 minutes. I'm sorry. This says 6 minutes. Okay. Okay. Yeah, we skipped that. Do you want to hear that? Okay. So much fun. Okay. Let's see if I can find the slide. Okay, so I'll try to do a quick run on this. Update constraints, what is this method good for? Normally, as I said before, you should update your constraints directly after the change occurred. And that's what Apple says in their own documents. If you want to change a constraint in response to a button tap, for example, then make that change directly in the button tap's action method. Why? Because this makes the control flow a lot easier to understand and will result in cleaner code. You know, you'll immediately know if the user tapped this button, then I deactivate this constraint. You immediately see the results of the user interaction. And then there are some cases where this might be a little bit too slow. I always need to wait for the snail to finish. Yeah. Okay. For example, when you change a huge number of constraints at the same time, or when you redundantly switch on and off the same constraints many times in a row, and in that case, only in that case, you should override update constraints. And then update all your constraints inside this method. And you don't do it in the buttons action method, you do it inside update constraints. And the reason is that the layout engine is a lot more efficient when it can handle all constraint changes as a batch. And you will have better performance in the end. So let's have a look at an example. Let's say we want to have 2 different layouts for the same screen. And we want to distinguish between these 2 layouts with a Boolean variable is centered layout. So this variable is true for the left layout, where we have the label centered with a fixed width, and it's false for the layout on the right side, where we just pin the label to the left side of the screen and to the right side of the screen. And now we want to toggle between these 2 layouts in code. How do we do that? Well, we override this update constraints method in our view. We need to make sure that at the end of update constraints, we always call the super implementation. It has to be at the end, not at the beginning, because this gives the system the opportunity to react to our constraint changes and do some adjustments itself. So you have to call it at the end. And now we activate and deactivate the constraints based on our Boolean variable here. So if we have the centered layout on the left side, then we activate the width constraint, and we activate the center constraint. And vice versa, of course, if centered layout is false, then they will be deactivated. And then we deactivate the leading constraint, and we deactivate the trailing constraint if we have the centered layout, and vice versa if we don't have the centered layout, if we have the right layout. Okay. So now, this method, update constraints, is called before each layout pass, but only if the constraints have been invalidated before, or by you if you call update constraints if needed. It's the same principle, by the way, normally you don't need to do that. It's the same principle as before. you need to invalidate constraints by calling set needs update constraints. This pushes up the flag for signaling that the constraints are not up to date anymore. Yeah, and of course, a good place to do that is in the property observer, it's set, and we can just check if the value has changed, and if it has changed, then we invalidate the constraints, and then next time the system will know that the constraints need to be updated. Update constraints will be called in the next layout pass. Again, only do this when you need to update a bunch of constraints at the same time, and you need better performance, which is not the case in 99% of the cases. Okay? All the other times, do just not touch these methods, please. All right. Cool, I have 5 more minutes. Yeah, this is just a recap. We have figured out what all these different methods do. I'll leave them on the screen for reference, and I'm up for any questions if you have any. Yeah. Well, here's the microphone.
Why overriding that method instead of calling the static method that an slayout constraint has that's called activate, and where you pass an array of constraints to activate? There's any difference between them, or it's quite equivalent?
What do you mean? There. Okay, I cannot see. You mean this method, right? Yes. So, why should we rephrase the question? Like, why should we use this approach?
Yeah, why using this method instead of, for example, using the static method to activate a bunch of constraints in a single step?
Yeah, I think it's basically for performance reasons again, because you have the same principle as before with the layout itself. That only you have this opportunity to invalidate the layout and to invalidate constraints in this case, and then they will only be called if they are invalid in a way. So that's less frequent, and also again only if you have a list like of maybe 20 constraints or something, or a very complex layout. And in that case, it doesn't make sense to always, because the question is when do you do that, right? You need to initiate this enabling, activating, and deactivating constraints thing. Oh. Oh. Yeah. Is this going to be broadcasted to the internet or something? Oh, I'm sorry. Okay. What was I about to say? Okay. So pretty much it's like the question is when do you trigger all of those batch constraint updates? You also need to do it at some point, and that's the question. Usually you would trigger that like at a point where it might happen, but then it'll happen over and over again, and yeah, you won't have the performance. I don't know. Is that kind of clear? More or less. Okay. Any more questions?